kernel of a ring homomorphism. We have already seen the kernel of a group homomorphism. So let's look at this. If f is a function which maps R to R prime, then the set of all those elements of R which are mapped to the additive identity of R prime is called the kernel of ring homomorphism. Okay, so this can be written as S is the kernel is equal to the set of elements of R such that f of R is equal to 0, where or let's say 0 prime, where 0 prime is the additive identity of R prime. Okay, let's look at it in more detail in terms of theorems. So let's look at the first theorem. If f maps R to R prime be a homomorphism, that is a ring homomorphism, then f of 0 is equal to 0, or to be more precise, 0 prime. And the second is f of minus a, or f of the inverse of an element of R is equal to minus f of a for all a belonging to R. Okay, now let's prove this. Now we know f of x can be written as f of x. There, f of x is equal to f of x. But this f of x can be written as f of x plus 0, right? Where x is from R, 0 is from R, for all x belonging to R, and 0 also belonging to R. Now, which means due to homomorphism, we can say f of x is equal to f of x plus f of 0. This we can split it like this. So here x belongs to R, x belongs to R, and 0 belongs to R. Okay. Now, since f of x belongs to R prime implies that f of x is equal to f of x plus 0 prime. That is 0 of the R prime. Now we have f of x equal to f of x plus f of 0. So let's do the substitution. So f of x plus f of 0 is equal to f of x plus 0 prime, right? Now these two get cancelled, left cancellation law. So we end up with f of 0 is equal to 0 prime. So 0 of R will map to 0 of the R prime. That is our first one. Second one is a plus minus a is equal to 0. An element of R added to its inverse will give us the additive identity for all a belonging to R. Now let's take the function of this. A plus minus a is equal to, this 0 can be written as 0 prime because we are taking the function. Let me split it into steps. So this will be f of 0, right? Now f of a plus minus a can be split into f of a plus f of minus a is equal to f of 0 is 0 prime. Okay. Now f of minus a is equal to, we take this to the other side, we end up with f of a minus. So we end up with the second property, f of minus a is equal to minus f of a. So that is our first theorem. Now let's look at the second theorem. The kernel of a homomorphism, ring homomorphism, from a ring R to a ring R prime is an ideal of R. Okay, so we already have seen what ideal means. So let's proceed. Let F map R to R prime be a ring homomorphism as f of 0 is equal to 0 prime. 0 belongs to the kernel of f. This comes from our previous theorem. So therefore, since 0, f of 0, or rather 0 from the R maps to 0 prime of R prime, kernel of f will never be an empty set, because at least it will have the additive identity. Okay, let x and y belong to kernel of f, which implies that f of x equal to 0 and f of y is equal to 0. So we have two elements which map to 0. Actually, I should say 0 prime. Now, if we take f of x minus y, that should also map to 0 prime. So let's see f of, we can write x minus y as x plus minus y, which can be split into f of x plus f of minus y. Then this becomes f of x minus f of y. And here we have f of x minus y. And f of x minus f of y is what? F of x is 0, f of y is 0. So that means this is 0, or rather 0 prime. Okay. So this was with respect to addition. Now let's look at the product. Let's say R belongs to R and X belongs to the kernel of F, which basically implies, based on the definition itself, that f of x times R is equal to f of x times f of R, which implies that f of x R is equal to, x is an element which belongs to kernel of f, so that is 0 prime times f of R, which implies f of x R is equal to 0 prime. Similarly, let's look at it the other way around. F of Rx is equal to f of R times f of x. But if x belongs to kernel of f, that means f of x maps to 0 prime. So f of R, which implies f of Rx is equal to 0. Now, since xr belongs to kernel of f and Rx belongs to kernel of f, implies that kernel of f is an ideal of R, because that is the condition, no? Both Rx and XR should belong to the ideal. Okay, so that is the second theorem. Now let's look at one more theorem. If f is a mapping from R to R prime is a homomorphism and A be an ideal of R, then f of A is an ideal of f of R. So there will be an ideal to ideal mapping. So here f of A would be equal to x belongs to R prime, where A belongs to A, such that x is equal to f of A. Remember, x belongs to R prime. A belongs to the ideal of R, such that x is equal to fa. Now, it's very clear that the identity, additive identity, will belong to f of A as, or rather 0 prime, as f of 0 is equal to 0 prime. Therefore, f of A is not an empty set. Now, again, let's take two elements x, y, belonging to f of a. X is equal to f of a, y is equal to f of b, where a and b belong to a. So therefore, x minus a belongs to f of a, because remember ideal is a subring, so it is closed, which implies a minus b belongs to normal. If R1 belongs to f of R, then there exists R belonging to R such that R1 is equal to f of R. So therefore, R1x is equal to f of R times f of, because here R1 is f of R and x is f of a. Now this would be equal to f of Ra. So R1x is equal to f of Ra, which implies that R1x belongs to f of a, since Ra belongs to a. And similarly, we can show that xR1 belongs to f of a. So again, xR1 belongs to f of a, R1x belongs to f of a. Therefore, f of a is an ideal of f of R. So that is kernel of ring homomorphism. That's it for now. Bye.